So hey guys, today I'll be discussing about AVL trees. So previously discussed about binary and binary search trees. So today I'll be talking about AVL trees. So what are AVL trees? AVL trees are binary trees which can balance itself according to the input. So what does this mean? Like we have seen in binary trees, like and binary search trees also. You can tell this a binary search tree. So what we have seen in binary search trees, like if the root node is, let's say, 10, the greater element will go to the right side of the root, the smaller element will go to the left side of the root. And again, something which is greater than 10 will come to this side, and this side something greater than, like, less than 10 will come this side. So let's say I enter 4, so this will come here. Next, let's say I enter 3, 3 will come here. 2, 2 will come here. So what we can see is like here it's like forming like a linked list. So I've seen like the search complexity of the time complexity of searching of the binary search tree is like log big O of log of n. But here we can see that it's forming, it is the best case. But here we can see according to input the search is the search complexity, like time complexity is changing, because if I had to search for true, I have to go through this whole linked list. But this is not like this is not like the big O of log of n. So let's say if my input is like sorted, increasing or decreasing doesn't matter. There's 1 2 3 4 5, I will get a right skewed tree. But this like this data structure doesn't have any property of tree. This is basically like a linked list. So the time complexity will be log O of n, sorry, I mean big O of n. So the property of the trees we can't use it here, right? Because yeah, and again, if my input is like decreasing order, then also I will get a skewed tree, like here 9 8 7 6 5 and 4 3. This is also like a linked list. So here we can't, and the property of the binary search tree, like the time complexity of searching, like which is big O of log of n, is not maintained. For this reason we will go for AVL trees. In AVL trees what happens is like every node, let me make another color, green. In AVL tree, in every node in every node in AVL tree has a balancing factor. So what is this balancing factor? Is the like difference of the height of the left subtree minus the height of the right subtree. This height is also height of the left subtree minus height of the right subtree, and the balancing factor should always be in a range of -1 0 and 1. Anything greater than anything, like if it doesn't maintain this balancing factor, any node, then we have to balance the tree. What does this mean? Let's say I have 10, I have 11, not say 11, like 20, 15, and here I have 1 6, and here I have 1 17. Okay, so the balancing factor of, let's find the balancing factor of each node. So here nothing is there in the left subtree, nothing is there in the right subtree, so the balancing factor is 0. Let's find the balancing factor of this, is also 0. let's find the balancing factor of this. This has only one right subtree, so the height of this right subtree is 1. Then it is 0 minus 1. It is minus 1, which is in the acceptable range. Let's find the balancing factor of 20. The balancing factor of 20 will be height of the left subtree. What is the height of the left subtree? 1, 2. 2 minus 0 is equals to 2. So we can see the balancing factor of this node is not in the range. Now let's find the balancing factor of this node. So this is 0. This height of this left subtree is 1 minus height of this right subtree will be 0, 1, 2. Sorry, 1, 2, 3. So it will be 3, which will be minus 2. So this tree is not balanced. Now we have to balance the tree, because you can see this node, sorry, I mean this node and this node is not having, they're having an abnormal balancing factor. Here it is 2, here it is minus 2. So let's find the culprit here. Let's say I have 20 here, and this is how it is done during coding. Like, you insert a tree and you like derive the balancing factor and then balance the tree. So here it is 20. Let's say you insert a tree here, a node here, this 30, and this is 40. So so you can see the balancing factor of this node will be 0 minus 2. Okay, so you can see that it is minus 2, the balance factor. So we have to rotate this node 20. So we have to rotate this node 20. So how can you fix this? So for this you have to, this 20 node has a problem in the right, so it will go in a left rotation. So it will be like 20 will be here, 30 will be here, and 40 will be here. So you can see the tree is balanced. Now we can find the balancing factor of this node will be 0, because 1 minus 1, 0. This is 0, this is 0. So it is balanced. So this is how we balance a tree. Like balance a BST to this is the binary. So, and I'll show you the right case. This is 40, this is 30, sorry, maybe it's a pen color. This is 30, this is 40, this is 50. So sorry, the 30, this is 20, this is 10. So this tree has a balancing factor, let's say 2 minus 0. This is 2. The balancing factor, this is 1 minus 0, 1, this is 0. So we can see the node which is having the problem is this node. So the node which is having the problem will go on a rotation. So this node has a problem in the left. So it will go on a right rotation. So what will the output? This will be 20, this is 10, this is 30. So you can see the tree is not balanced. This is a wheel tree. And also let's find the balance factor of each node. This 0, 0, 0. We can say so thus we can see that each and every node is balanced. So now how we can code this? So let's say we have a node like this, C, A, and this is T1 and T2. Now let's say C2. Okay, just a minute. So we have a node here, P, A have T1, T2, we have T3, T4. Let's say we have insert a node N in either a T1 or T2. Okay, and for this reason we traverse upwards from this node which we have entered here upwards till we find a node which has a abnormal balancing factor. So we traverse upwards like this, and we find that C has a abnormal balancing factor. So what we do is we traverse downwards and just capture first two movements, first two movements. This is the first movement, this second movement. So if we can see that this is left, this is left, this is LL case. Okay, because how can I prove that this is LL case? See, what we first saw is like n. Let's say n was first inserted in T1 or T2. So we traverse upwards till we find a node which has a abnormal balancing factor. Let's say we find the abnormal balancing factor, the node with abnormal balancing factor as C. So what we do is we traverse downwards and capture the first two movements. So this we first go down to the first two movements towards the n node which we inserted. So first this and this. So we can see first left, then again it's left. B is left, C is left. So this is an LL case. So how can we find it is an LL case? It is LL case because the balancing factor of the affected node is greater than 1. How can I say this? Greater than 1 because 2 minus 0, or it can be 3 minus 1. It can be 3 minus, it cannot be 3 minus 5 because I am getting minus. If it is a LL case, the first L, to get the first L, we need to find the balancing factor of the C. If it is a positive number, then it is a left case. It is a negative number, it is a right case. How we can say that? This is 2, 2, this is 3, minus 1. This is always positive if we go left. And then if you go right, it is always like negative. Why? The 1 minus 5 is minus 4. This is the reason. So here I am writing the condition for LL case will be the balancing factor will be always positive, balancing factor will be greater than 1. This is the first thing. The second thing, this b dot data item which we inserted, which is the nth node, n dot data will be less than b dot data. That is why we send it to the left side of the b, because in dot data is less than b dot data. So how can we fix this problem? How can we fix this, like what happened here, like the balancing factor of C? So you can see this LL case. So C has a problem with the balancing factor of C has a balancing factor of abnormal balancing factor. So if C has a problem, we will rotate this C only one rotation, right rotation. So what will happen is like, let me copy this. So B will come here. B will have with the child A. This will have T1, T2, which will be untouched. Then we will have C as B's child. T3 will be on this side. And T4 will be on this side. So you can see this totally balanced. So how we did this? Let me write the code. We will first, what we did is we first made the right child of B as C. So let me store the T3. T3 is C dot left dot B dot C dot left is this dot right. So I have saved my T3. In place of T3 I will give C. So C dot left dot right will be C. Okay, so I have changed it to C. Now C dot left will be T3. So it's completed because C dot left is T3 and C already had a right child of T4. So it is done. So this will be the code for the right rotation, single right rotation of this node.